This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, we're live and recording, so we're getting to the lecture. As I said, we're kind of done with the majority of the theory, although there's one new trick that I'll teach you today. What we're going to do today mostly is go through two examples of a Brayton cycle and do them in as much detail as we can, with me scribbling down. Now, these worked examples are also available in the LMS notes, so if you want them to go through later, they're there. I'm going to go back to the propulsion cycle, which is the modification of the Brayton cycle that lets you get thrust out rather than turbine work. Just briefly, so that we can go through this problem. So the Brayton cycle was isentropic compression, isentropic expansion. That was your compressor and your turbine. Between those, you had a combustion chamber that was adding heat at a constant pressure. That's the key elements to a Brayton cycle or a gas turbine cycle. In the propulsion cycle, you have a diffuser at the front and a nozzle at the back. The diffuser in the ideal cycle is also isentropic compression, and the nozzle, 5 to 6, is also isentropic expansion. So it's the same maths in the sense that you have the isentropic compression, isentropic expansion. If you want to find out the temperatures at point 1 and point 2, you're using the air standard T2 on T1 equals P2 on P1, gamma to the minus 1 on gamma. I say that like it's natural that you would have memorized it by now. This is an equation you will be given on your equation sheet. You need to recognize it and know when to use it. So let's have a look at those different components. Everything I've just said. The last step that people will get, sometimes they get a little bit caught up in, is this isobaric or constant pressure cooling. What this represents here is effectively a dotted line, which is to say the exhaust that goes out one end of the gas turbine eventually reaches the temperature and pressure of the atmosphere, and what's coming in the front of the turbine is at the temperature and pressure of the atmosphere. And so going from 6 to 1 doesn't happen inside the machine. It's a dotted line to complete the cycle so that we can keep track of the mass flow rate through these components. When we've done nozzles and diffusers so far, we've done them in the tutorials and we've done them in the lectures, their job is to change the velocity of the fluid. And so what you're doing is converting enthalpy into kinetic energy or kinetic energy into enthalpy. There's no heat transfer and no work done. So you've got Q minus W equals delta H plus delta KE. That's the important bit. This is one of those ones where you can't just cross off the KE, the delta kinetic energy. So we'll play with those in the worked example. We'll have a worked example of a gas turbine and a worked example of a propulsion gas turbine. So we'll do one of those diffuser examples. These equations, when you're dealing with air, you're in an ideal gas. When you're dealing with an ideal gas on an isentropic process, you have three friends for working out what happens over an isentropic process. So if you need to determine the properties at state 2, and I tell you it's an isentropic process, these are your map to get there. And either you'll be given a volume ratio or a pressure ratio to be finding temperature. So down here, T2 on T1 is V1 on V2 to the gamma minus 1. T2 on T1 is P2 on P1 to the gamma minus 1 on gamma. So these two, this one you'll be using in an Otto cycle because you are the engine is described to you in terms of the volume ratio of the cylinders, of the cylinder from bottom dead center to top dead center. This one is what you use for a gas turbine because the gas turbine is described to you in terms of the pressure ratio from the intake of the compressor to the combustion chamber, which is to say the pressure ratio from if it were not a propulsion one, from 1 to 3, and if it is a propulsion one, from 2 to 3. So they make our life a little bit easier because the very first thing is someone tells you, I've got a gas turbine that's sitting in the outside world, so it's sucking in air at 1 atmosphere and 27 degrees, and it's got a compression ratio of 35. Tell me the temperature at the end of the compressor. Adiabatic process, isentropic adiabatic process. I grab this guy. You've told me it's air, and so I've got gamma because gamma is a property of the air. I can then solve for the temperature. So let's play around with that pressure ratio a little bit in the same way as we played around with the compression ratio of the car engine, and we had a look at its efficiency. If I'm operating between two temperatures, there's a neat thing that happens with the pressure ratio. Not only do we have a graph that shows that the efficiency, the ideal efficiency of the Brayton cycle keeps going up, it is also possible, as you set the pressure ratio for a fixed temperature difference, you are setting the amount of work that comes out. And what's interesting, or at least what's interesting to me, is that doesn't keep increasing into infinity. There is a peak for the amount of work that comes out. So these boxes here represent a small pressure ratio, a medium pressure ratio, and a large pressure ratio. Sorry, other way around. Small pressure ratio, medium pressure ratio, large pressure ratio, and there is an optimum, and the optimum can actually be analytically expressed if you're trying to optimize for the work output. There's one last concept that we give a name to. The turbine drives the compressor. So they're connected on a shaft in the machine. If it's a gas turbine that's powering this powering a generator to make electricity, there's work that goes out to that generator to make the electricity, just in the shaft, but also the turbine is powering the compressor. So the work that went into the compressor, the only place it came from was stuff that the turbine was doing, and anything you've got left over is what gets useful work, net work out of the system. So we refer to the back work ratio as the compressor work over the turbine work, and it can be more than a half of the turbine work. And this is where the efficiencies of this system make a big difference. Because there comes a point where if the turbine's a little bit inefficient, it doesn't have enough work to run the compressor. As we were describing propulsion, I'm going through these concepts quickly, I understand. So as we were describing propulsion, I was saying that the main job of a propulsion engine is to increase the momentum of the fluid between what came into the engine and what goes out of the engine. So that's the way you get your force, that's where you get your thrust, your acceleration, is the difference in momentum in and momentum out, which is a little bit different to what we've been handling in thermo up until now, because we've just been handling heat transfer and work. And if you think about the job that a gas turbine is doing when it's a propulsion gas turbine, the turbine isn't connected to anything else outside of the machine. It's only connected to the compressor. So in a propulsion gas turbine, the turbine's only work output is to run the compressor. And the extra energy that's left over is in the enthalpy of the working fluid gets converted into velocity. So that's where we use that nozzle to maximize the velocity of the gases coming out the back. So thrust as a force is mass flow times velocity. This V here is not volume, it's velocity. And so the delta force is m dot V exit V inlet. And when you're cruising at constant speed, that force balance, so that thrust, if it were unbalanced, would be producing acceleration. What it's balancing against during flight is the drag of the aircraft. So when you're at steady speed, this force is exactly balancing the air friction drag on the aircraft. Those are little ideas for later. It's one of the things that makes going up to very, very, very high altitudes much more efficient. The other thing that makes going up to high altitudes more efficient is the air that's coming into the system is cold. So it might be minus 50, minus 60 degrees as opposed to 30 degrees or 20 degrees. That difference makes a big difference in the overall efficiency. So getting up high in the atmosphere for a gas turbine propulsion system is actually very good for efficiency. Turning that into power is also a little bit tricky. And what you do is multiply that force by the average velocity of the plane. So these are introducing a series of equations that we haven't played around with much, which is why we're going to have a worked example. I want to get the ideas down because there's another idea that I need to introduce to you. I say that we're done with ideas and then I give you lots of ideas. Anyways. So the net work inside the engine is 0, but you do have a power. It's very difficult to define efficiency for a system like that unless you come up with a concept called propulsive efficiency, which is to say, what is my propulsive power divided by the rate at which I'm burning fuel? And then we do that because in the thermodynamic cycle, the work out of the thermodynamic cycle in terms of shaft work is exactly consumed by the compressor. So I should draw it for you guys. The work out of the turbine is exactly consumed by the compressor, and so we don't have this sense of net work out. But the machine does something. The machine makes a change. It makes a change in velocity. There is a force and a distance, and you can put all that together as a power. So efficiency in propulsion is talked about propulsive efficiency, which is the work done divided by the fuel burn, effectively, the heat input. Before we get onto the example, so that's the finishing off of what's in aircraft engines, what's in propulsion engines. The two examples that we're going to have, one is a normal gas turbine example, and the other is a propulsion gas turbine example. We're going to play with or experiment with different tools so that you are familiar with using the tools. When I've been introducing CP delta T as a tool for enthalpy, it came with a caveat. It came with a please remember that by saying CP delta T, I'm implying that CP is a constant. And I did tell you that CP changes with temperature. So if we're changing 100, 200 degrees, that approximation is okay. If we're changing 1,000 degrees, which can happen in a compressor, or 800 degrees, you end up with some errors. And so there is a tool or a table that one can use. Yay, another table. There's a table that one can use and a trick that one can use if you can't assume that CP is constant. So your three options, I'm going to put a couple of things up on the screen. First we'll jump up here. Good. For ideal gas, you can do CP, for ideal gas delta H, you can do CP delta T, where CP is at cold air. You can do CP delta T, where CP is the average of T2 and T1 temperature, or H2 and H1. So it's a delta T. If I knew T2 and T1, that would be easy. If I don't, I have to guess and then go back. So that becomes an iterative process that is a little bit tricky to do. But usually your first guess, if you know you're dealing with a gas turbine, you know your output's going to be of order 800, 900, 1,000 from the compressor, you have a good idea, once you've done a few of the questions, you would have a good idea approximately how big this number is, and your average will be pretty close. The last one is to not assume constant CP. How do I do that? What that means is now I tabulate a whole bunch of stuff. For an ideal gas, I can have an ideal air table that lists temperature, enthalpy, and two new guys, PR and VR. And these are the guys that we use to move around this table. And I'll show you how. I'll show you an example of the table. This table is in the one that you can download off the LMS, if you want to have a closer look at it. Ideal gas properties of air. Column is temperature. Good point. Okay, we'll try again. Ideal gas properties of air. The main driving column is temperature, and it's also our main goal. Usually when we're trying to analyze one of these processes, we're interested in what's temperature 2 or what's enthalpy 2. So we know temperature 1, we know, for example, an isentropic process or not, and so our goal is to find what's the state at 2. So down the left-hand side you've got enthalpy, temperature, you've got enthalpy, which is saying that for an ideal gas, enthalpy is determined by temperature. You've got internal energy, and you've got these two new guys, reduced pressure and reduced specific volume. They are ones that we've not yet played with. The equation will be in the slides in about 2 taps time, but I'm going to just jump between projector and screen a couple of times. We have a way of jumping around this table if a process is isentropic. So most of the time I'm on this table, it's because I wanted to use something like T2 on T1 equals P2 on... I wanted to use something like this. That was my goal. And I'm limited in using this, or I don't know, this guy. I have this rule that for an isentropic process, this new definition of reduced pressure and the ratio, so the ratio of pressure is equal to the ratio for an isentropic process is equal to the ratio of PR2 and PR1. The ratio of specific volumes is equal to the ratio of reduced specific volumes. That doesn't look like much of an interesting thing. I'm telling you the equations now because we will use them in the first example. So bear with me, we're just about to do a worked example with these ideas, and you can see how I would jump around a table with this. I'm now going to jump back to the table and show you a trick. If you told me, so the equation I wanted to use is only valid for constant specific heats, and the equation, so if I've got variable specific heats, and that's the code word, I can't use that equation. If you told me that we were starting at 300 Kelvin and my pressure ratio was 35, then for an isentropic process, my PR ratio is 35 as well. So I've got PR here. If I times that by 35, I move down the table. 35 times 1 is around about 35. I mean, I would do it exactly, but for the purposes of this exercise, I'll come down the table, come down the table, come down the table, and it's PR column. I haven't got up to 35 yet, so I go back up. And here's my PR column. I come down, 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 and what I have is 35 times 1.3 might be a little bit bigger, so somewhere around here, let's say. then I can look up my temperature at the end of that isentropic compression. So we will do that twice in the worked example, but that's how the tool is used. The catchphrase, the key phrase for this is if I say using constant specific heats, you're okay with the equations. If I say using variable specific heats, it says it's an indicator that says use the tables. You can quite easily determine the magnitude of the error between the two because you've got access to the equations and the tables. So you can solve the problem with both and say this is a 1% difference, so I don't care. This is a 10% difference, so maybe I care. This is a 30% difference, so yes, I absolutely care. On a cycle, when the whole cycle is being analysed and you come back to this, so it should do the way you see, when the whole cycle is analysed and you come back to the starting point, often the errors cancel out. So one of the reasons why you'll find us using constant specific heat is because the analysis for one component might have an error, but by the time I've gone up and back, those errors can balance out, but not always. So keep an eye open for when I'm saying constant specific heat or variable specific heat. That's your trigger to say I'm using a table or an equation. All right, let's get back to the notes. What I've drawn up there, let's take our time to look at the graph. We said that we would have an ideal cycle, and our ideal cycles would have the best possible process for any step, which implies that the real cycle has a difference to that. When I introduced compressors and turbines and entropy, I made the point that if I have losses, my compressor and my turbine won't go straight up and down on the graph, on the TS graph. They will increase in entropy a little bit. So we'll map our way around this guy. This is a Brayton cycle. This is a gas turbine cycle. So on a TS diagram, I start from the beginning of my compressor. My ideal cycle is isentropic here, then add some heat, and then isentropic here, and then let some heat out. If I have a real compressor and a real turbine, as opposed to an ideal compressor and an ideal turbine, the real compressor will have some friction, have some losses, and have some heat transfer, and as a result, I will increase in entropy a little bit during that process. So the real process is no longer an isentropic process, which means I have no magic equations for it. If I have a real turbine, it's trying to do some work, but it's fighting against friction and heat transfer. And as a result, the result is not isentropic, the result is a little bit more entropy. When we think about it in terms of the work done, so Q minus W equals delta H, on the isentropic process, or in the ideal gas process, we drop the Q, we're saying they're adiabatic, maybe this breaks down, but we're looking at a delta H. The work required to run this guy is a CP delta T, which is to say, my delta T is here, and if I have losses and friction and whatever, my T2A is higher, is bigger, which means the amount of work required to run an inefficient compressor is more. It's harder to run an inefficient machine. On the turbine, which is trying to do work, is trying to release energy and release work, the amount of work I can get out is delta T times CP, 3 to 4S is the temperature, delta T. And if I have losses, my delta T is smaller, so I get less work out. So if I put both of those together, if I have a slightly inefficient compressor, I start this journey at a higher temperature, then I add my fuel temperature up to here, and then I have a slightly inefficient turbine, and then I release my heat out there. So as an overall result of the net work out, I have less work out of here, I did more work here, my efficiency has dropped because of the inefficiencies of the components in the machine. You follow that last step? So, how do I write that down? I've said here, a compressor, assuming a compressor efficiency of this and a turbine efficiency of that. It would help if I had a way to represent the efficiency of a turbine or a compressor in an entropy sense. So we've talked about the efficiency of a cycle. We've talked about the efficiency of a cycle because there's net work out over the heat input. But for a component, we refer to the isentropic efficiency, which is the actual output divided by the best possible output if it's doing work, or, so the efficiency has to be less than 100, right? So the ratio, if I'm doing a compressor, the notation for it is a 2 for the second law. Okay, so it's referring to the second law in entropy. For a compressor, we're talking about if it's more work done to run a bad compressor, the actual work goes on the bottom and the ideal work goes on the top. For a turbine, we flip that over. If it's less work out from a real one, then the actual work goes on top and the isentropic work goes on the bottom. So if you can't memorize the equations, which is okay, remember them by logic. The number has to be less than 1. The best possible work for a compressor is smaller than the actual work. The best possible output from a turbine is bigger than the actual output. But what do I do with these to actually solve a problem? I've just written them in terms of work. For a compressor or a turbine, we've got the work being delta H. So I evaluate these guys with my enthalpy 2 and my enthalpy 1, with my difference in enthalpy. And so I would be writing H2S minus H1 over H2A minus H1, for example. And I could substitute in CP T2S minus T1 over CP T2A minus T1, and then I can drop those out. So I begin with an expression in terms of work. Because it's one process over a compressor, I'm describing the work done to power the compressor in terms of delta H. Because I'm dealing with an ideal gas, I can turn it into a CP delta T. And when I go back to my little graph of a compressor, there's my isentropic process from T1 to T2. There's my real process to 2A. I've got T2A. This now gives me a map that says all of my useful tools have been built up for isentropic things, but I know that all things are real and so have losses, etc. So either I can measure the actual temperature and compare it to what the best possible temperature should have been, or if I knew the efficiency of the machine, I can determine the isentropic work, and with the number of the efficiency of the machine, I can tell you what the actual work will be. So I can use this to solve, I can I can measure the actual and know my theory well enough to be able to calculate the best possible, and then tell you this, which is to say I can tell you how efficient my compressor is or not. It could be 90%, 80%, 70%, 60%, whatever. Or if I've given this, which is more commonly the case, then I can use that to solve for T2A. Because T2S, I've got equations for. Is that still on the screen? Yeah. T2S, I've got equations for. So we'll go back to the question and now see how the question was written. The question says, assuming a compressor efficiency of 80%, a turbine efficiency of 85%. Those are the numbers that I've just told you about. Determine the backwork ratio, the thermal efficiency, and the turbine exit temperature. Where's the turbine exit temperature? Compressor, combustor, turbine. This is the ideal turbine exit temperature. This is the actual turbine exit temperature. So if I can find my way to point 4 and determine its state, I can tell you the temperature. Using air standard assumptions instead of cold air standard assumptions is a code word, which is why I've underlined it. It's a code word that cold air standard assumptions tells you I can assume Cp is constant at the cold air temperature. Air standard assumptions tells you I should be using an ideal gas table, the one that I just introduced. So this problem, we're going to be playing with isentropic efficiency, and we're going to be playing with moving around on the table. You get those up there, these up, and we'll be using this guy. Okay, so let's solve this. Where do we begin? Where do we begin? We begin in the same place we always begin. That's on screen? Ow. So, Brayton's cycle, real as opposed to ideal. I want to copy over all the things I've been told in that question, and I'll start with the diagram. So it won't be until I'm about here. It won't be until I'm about here that I actually start to solve anything. I'm not going to jump in and go, oh, I need an isentropic compression ratio. Don't do anything until you've got a nice big diagram, T, S, and we were told that I had T inlet, so with T in equals T1 equals 300 Kelvin, and I was told that T max, I need a graph now, there's my isentropic graph, constant pressure lines, 1, 2, 3, 4. So, I've done my graph. I'm not finished yet, but I'll get there. T max is T3. The highest temperature I can reach is the temperature at the end of my combustion chamber, equals 1300 Kelvin. I've got a pressure ratio, equals P2 on P1, equals P3 on P4, equals 8. And I've been given the compressor efficiency of 0.8 and the turbine efficiency of 0.85. So as I write these down, I better put on a 2A and a 4A. And as soon as I start writing down A's, I tend to write down S as well to remind me. Assumptions. A lot of the assumptions can be all wrapped up into air standard cycle. And tools, I use first law I'll use ideal gas tables. Am I still on screen? Yep. With the reduced pressure. That should be enough for there. And I haven't even written down what I want to find. Find A, the back work ratio, B, the thermal efficiency, and C, T4 actual, the turbine exit temperature. So I've used up about a third of the page already, just on writing down the question, and I've got myself a few marks. And now we need to start solving. Is that going to move that? Yep, good. No one screamed. The trick to this, the trick to most cycle problems, is to solve the isentropic cycle first. You've got the tools for that. So first, solve isentropic. Then use isentropic efficiency to get actuals. Okay, so let's go. For point 1, so what we're going to do is work our way around this cycle. This way, this way, this way, from 1 to 2 to 3 to 4. We know 1, we know the pressure ratio to 2, which means we will be able to work out the pressure at 2. We know that the pressure is the same at 3 as it is at 2, because it's a constant pressure process. So that's our trick. We know the temperature at 3, and then we know the pressure ratio here to get back down to 4 again. So we have all the tools and we have all the information. We just need to do the maths now. And the first time you see the maths, you go, oh, that's where I use this, that's where I use that. Later on it becomes more familiar. So at T1 equals 300 Kelvin, H1 and PR1. Why do I need these guys? So why am I not reaching for CP delta T? Because I've been told that I'm using the air standard, not the cold air standard. So what we do is we come to here. There's my temperature, my enthalpy, and my reduced pressure. So my enthalpy, I'll write them down, 300, 1.19 and 1.386. I'll come back on. I won't jump back to the slide every single time, but I will jump a couple of times. No, I want DocCam. Yeah? Good. Okay. All right. So at this point, I haven't done any maths. I've just looked up a table. I was given the temperature. I didn't even have a pressure there. Do you notice this yet? So, with this is my tool. This is the thing that I'm going to use to jump around. I've been told the pressure ratio is 8. So, I want to get to 2. By getting this guy, I'm done. I'm finished with point 1. That's kind of neat. I haven't had to do any maths, and I've already finished with point 1. I've got my enthalpy. The point where I get my enthalpy, we're moving to the next point. So we've got PR2 on PR1 equals P2 on P1 equals 8. So I can say PR2 equals 8 times 1.386 equals 11.09, if you were to put it in. So now what I need to do to get to 2S, I need to look up PR2, and I'll get T2S and H2S. So 11.09 is my number. This is the last time I'll jump onto the table, because I'll do this again for the turbine, but bear with me. So my number was 11.09. I'm scrolling down, scrolling down, scrolling down, scrolling down. I could do the interpolation, but I'm going to suggest, for the sake of this calculation, that 11.09 is pretty close to 11.10. And so there's my enthalpy, and there's my temperature. So we had from 300 to the pressure ratio, to the reduced pressure, then using the pressure ratio to take me to the new pressure ratio for the isentropic process only. I can only use PR2 on PR1 equals P2 on P1 for an isentropic process. I can get enthalpy and I can get temperature. Okay, now we'll whiz through. This finishes my job for point 2. At that same pressure, well actually, sorry, importantly, I don't have I know that pressure 3 is at pressure 2, but using the ideal gas tables, I just need the temperature. So at T3, if I were to look up the tables at 1300 Kelvin, I would get H3 equals 1395.97 kilojoules per kilogram. I would get PR3 equals 330.9. And so PR4 is equal to P4 on P3 times PR3, which is equal to 1 on 8 times this 330.9, which is equal to 41.36. This is going. This is now going from a high on the table down in PR, which will then give me H4S and T4S. H4S is 770 Kelvin and T4S is 789.37 kilojoules per kilogram. So at this point, by the end of this page, I've got the isentropic enthalpies and the isentropic temperatures for 1, 2, 3, and 4. If I want to get to the back work, if I want to get to anything actual, I now need to use the compressor efficiency and the turbine efficiency to get to T2A and or to H2A and H4A. So now use this guy. The compressor work is H2 minus H1. I have both of those, H2S. I have both of those. 544.36 minus 300.19 equals 244.16. And the turbine work, I have all the numbers I need, equals H3 minus H4S, equals 1395.97 minus 789.37, equals 606.6 kilojoules. So the turbine is doing more work than the compressor, which is where this back work ratio comes from. The ideal, this is kilojoules per kilogram. I could work out an ideal back work ratio, which is to say BW would be work compressor over work turbine. If I put those numbers in, I get 40.3%. Ideal. That doesn't answer the question yet. And I could also work in the heat in and the ideal thermal efficiency from these points, but they're not solving the problem. So what I need now is to go to my compressor work actual equals my compressor work isentropic over my efficiency. My turbine work actual, this is the equations that I put up before, reorganize equals my turbine work times my turbine work isentropic. So note, because of the different way up, because the definitions for efficiency were swapped, these guys are different when you write them down. This will give me 244.16. My actual turbine work should be bigger. So, my actual turbine work should be smaller. Now that I have these, I have all the information I need to solve the problem. So for A, the backwork ratio, 305.2 on 514.661 is 59.2%. Look at the difference. The ideal backwork ratio, the compressor, the turbine, was only needed to use 40% of its work to run the compressor, but with an inefficient compressor and an inefficient turbine, that's gone up to 60%. For B, to solve B, I need the heat input. So I've got the network out. And I'm going to need H2A so that I can get H3 minus H2A equals Q23. So the heat input is this guy. So if I'm going to get H2A, I need to go back to this this compressor work. So I determined up here the actual compressor work. That's H2A minus H1. And I know H1 because I looked it up from the tables because H1 was just defined. So with this, if I substitute in here and here, I can solve this for H2A equals 605.39. And then with that, I can get Q in. And with, then I've got H3 now and I've got H2A now. I can plug that into 790.58. And now I have all the bits I need for the thermal efficiency, which is to say work turbine minus work compressor over heat in. And here, if I put all those numbers in, you get 26.6%. So thermal efficiency of 26.6%. Doesn't sound very big. A pressure ratio of 8 is not very big. Not quite finished yet. We've still got to answer part C, which is to say, use the actual turbine work. My goal at part C was to get the turbine outlet temperature. So use this guy, and I've got H3 minus H4A. I want to find H4A so that I can then look up T4A from the tables. So rearrange that, and I'll have H4A equals H3 minus the turbine work equals 880.36 kilojoules per kilogram. And with this, I could look up from ideal air table T4A equals 853 Kelvin. Done. So that is all the extra stuff that I could fit or squeeze into a gas turbine cycle. I'm going to get as far as I can into the propulsion cycle. The main place I want to go in the propulsion cycle is doing a nozzle at least once. The rest of the tricks. Now the gas turbine problem we're about to solve. Let's get this up on screen. Go as fast as I can without losing you completely. Come back. So we give you all the information you could possibly ever need to plug in, but the difference here is we're saying cold air standard assumptions, and we've got ideal processes. So this is now, the difference to this guy versus the previous guy is everything is isentropic. I've got no, for you, I've got no real processes on the nozzle or the compressor. And the other difference, I'm saying cold air standard assumptions, which means that I can use Cp delta T instead of the tables that we just did. So this one, moving around, is all about the equations. If this thing times out on me before I get to the end of a diffuser, I want to make the point. I want to make the point out loud, on record, and to your faces. The most common thing to go wrong with a kinetic energy problem is units. The units of kinetic energy get solved in joules, and almost everything else we're dealing with gets solved in kilojoules. So you're sitting there going kinetic energy, about velocity. You turn it into a number. You solve your enthalpy. You solve it into a number and it's kilojoules. You try to convert my kilojoules to joules without realizing you're off by 3 orders of magnitude and your number makes no sense. Or you don't notice that your number makes no sense and you write it down and you wonder why you got nothing, or a minus 1 or 2 marks. It's the most common thing to go wrong, so I'll try to do one. Just gonna go away. Okay, let's get up. I'll try to get to the nozzle as quick as we can. The problem had a propulsion cycle, as always. These notes are in. We're up in the sky, so we're minus 40 degrees. These notes are in the LMS, and if we run out of time, I'm very happy to go through.
You're showing the slides still.
I am showing the slides still. Thank you. I've got Tmax, Tmin, 1093 degrees C for the Tmax, T4 now. I've got a diffuser, so 1, 2, 3, 4, 5, 6. Starts up in the sky, minus 40. Maximum combustion temperature, 1093 degrees Celsius. And it says find Tp at 5. Here, at the end of the turbine, velocity, oh boy, at 6, and propulsion efficiency because all the data is given. I know I won't get that far, so let's, how far can we get? If we begin to map our way through here, we've got T1 equals 233 Kelvin, T4 equals 1366 Kelvin, V aircraft equals, the V aircraft was given to you in kilometers per hour and you can't use that. So I need to go to meters per second. From 1 to 2, this is the one that I want to get up on screen before we run out of time. H2, so what I'm saying is it's a diffuser. So this is a diffuser. This is something that looks like that. It slows fast gas down. You were given how fast the plane is flying. That is how fast the gases are hitting the diffuser. So this is your incoming kinetic energy at 1. Its job is to slow it down to not very much here and turn all that into enthalpy. And so what we get is no heat transfer and no work. Isentropic process, adiabatic process. So Q minus W, 0, 0. Delta H plus delta KE. So I've got H, am I off the screen now? No. I've got H2 plus V squared 1, 2 on 2. Oh. V squared 2 on 2 equals H1 plus V1 squared on 2. The assumption here is the diffuser's job is to take the velocity down to approximately 0. It won't be exactly, obviously. So what I do is I get these guys together as a Cp T2 minus T1 minus V1 squared on 2 equals 0. If I rearrange this, I get T2 equals T1 plus V1 squared on 2Cp. I plug all my numbers in and I'll end up with 266.6 Kelvin, at which point I am done with finding point 2. The moment that I have the temperature on the map, I'm done, I'm good. This number here